Greetings A&P2 and welcome to your Wednesday virtual class. Remember, this lecture is going to be uploaded in several portions, so be sure to look for all the parts of the sequence. It should end with a discussion of what happens when you smoke. All right, so get ready, take good notes, and I'll see you after Thanksgiving. Bye. All right, so we're going to get started once again with lung volumes and capacities. So we'll be looking at a graph of all the various lung volumes and capacities in a minute, but first let's talk about this concept known as the tidal volume. Tidal volume is the amount that you inhale or the amount that you exhale with a normal quiet inhalation and quiet exhalation. So remember, when you inhale with the tidal volume, you're really only moving your diaphragm and also using your external intercostal muscles. And then the passive exhale, the passive tidal volume for exhale, is going to be just relaxation of those muscles. So doing that, you usually will inhale about 500 milliliters of air, or you would exhale about 500 milliliters of air. So the minute ventilation is the total amount of air that's inhaled and exhaled every single minute. Normal people, 12 breaths per minute. It really depends on you, but that would give a minute ventilation of about 6 liters per minute. All right, so here we see our graph of the lung volumes and lung capacities. So let's just quickly work our way through the graph. We're going to come back to some of these terms again, but first, really want to focus in on this idea of the tidal volume. So here we see an increase in the tidal volume, and here we see a decrease in the tidal volume. All right. So we look at increase and we look at decrease. So we have an inhale and we also have an exhale. All right. As we continue to inhale past that tidal volume, right, as we continue to inhale, so once again, I don't know why that's doing that. We inhale past the tidal volume, and then you can continue to inhale even more, right, till you reach the maximum amount that you could possibly inhale. Okay, so this maximum, or this amount that you could inhale after a normal tidal inhale, is known as the inspiratory reserve volume. All right. So there will be a total amount that you could possibly inhale. That's the inspiratory capacity. IC stands for inspiratory capacity, and the inspiratory capacity is equal to the tidal volume plus, sorry guys, it's equal to the tidal volume plus the inspiratory reserve volume. All right. All right, then once you've inhaled as much as you possibly can, the first that you will exhale once again will be that inspiratory reserve volume. So you'll exhale the inspiratory reserve volume, then you'll continue to exhale and you'll exhale that tidal volume, and then you could continue to exhale once again. Continue to exhale until you have exhaled as much as you possibly can. That amount is known as the expiratory reserve volume. So we have our inspiratory reserve volume, we have our tidal volume, and we have our expiratory reserve volume. That accounts for the total amount of air that you can physically circulate through your lungs, and that's known as the vital capacity, or VC, vital capacity. So vital capacity is equal to the inspiratory reserve volume plus the tidal volume plus the expiratory reserve volume. Or you could say that the vital capacity is equal to the inspiratory capacity plus the expiratory reserve volume. Remember, the inspiratory capacity is equal to the inspiratory reserve volume plus the tidal volume. All right, now that's obviously not all that all the air that you have in your lungs. There's also this reserve volume. that can only be indirectly measured. All right, so let me remind you of one feature that I talked about on Monday today, known as the anatomical dead space. Only about 70% of the tidal volume actually gets down all the way to the respiratory zone. That's the area where you can physically get gas exchange. So if we look at this, if we know that an average tidal volume is about 500 milliliters, so we have 500 milliliters, and we multiply that times 0.7, 70%, that's going to give us about 350 milliliters. That means that's the amount of air that actually gets all the way down into the alveoli. Alveoli. All right, or the respiratory zone. The rest, 150 milliliters, will be found in that anatomical dead space. Right? Doesn't undergo respiratory gas exchange. So sometimes, instead of talking about the minute ventilation, which is the total amount of air that circulates, we may want to calculate the alveolar ventilation. So that if you have 12 breaths per minute times 350 milliliters will give you the actual volume of air that you circulate through your respiratory zone. All right, so let's go back to some of these lung volumes. We've talked a lot about tidal volume. So tidal volume is the total amount that goes in, and it doesn't matter for the tidal volume whether it's in the anatomic dead space or the inspiratory, the respiratory zone. So that's the normal amount that you can passively inhale or exhale. The inspiratory reserve volume is after you inhale your normal tidal volume, you can continue to breathe in past that point to give you your inspiratory reserve volume. There's also an expiratory reserve volume. So remember, the expiratory reserve volume is what you can exhale forcefully after a normal exhale. So you have first a normal tidal exhale, and then after you do that, you exhale forcefully. And it's how much more you could possibly exhale. Right? And then, of course, we still have that residual volume, the air that's remaining in the lungs after you have completely exhaled all of that expiratory reserve volume. So once again, some calculations I've already introduced you to. The vital capacity is equal to the inspiratory reserve volume plus the tidal volume plus the expiratory reserve volume. The total lung capacity is that vital capacity plus the residual volume. So once again, we can see all of our different lung volumes and lung capacities. You should be familiar with the definitions of these various volumes and also the calculations. So make sure that you know how to do the calculation for inspiratory capacity and also vital capacity and also total lung capacity, and know how they relate to each other. All right. So when we were first beginning to talk about pulmonary ventilation on Monday, I introduced a law called Boyle's Law, and it's one that you're very familiar with. That's the inverse relationship between the size of a container and the pressure in the container. Now we're going to get into some gas laws that are really important for actually moving air from the alveolar space and into the lungs themselves. Into the capillaries that surround the lungs themselves. All right, so we begin with Dalton's law. And Dalton's law states that each gas in a mixture exerts its own pressure as if there are no other gases present. All right, so that's kind of hard to think about. But remember, you have multiple gases that are found in air. All right, first we have nitrogen gas, N2, so we have nitrogen. We have oxygen, it's a gas. We have water vapor, is a gas that's found in air. You have carbon dioxide as a gas that's found in air, and then there are lots of other gases. All right, so air is a mixture of gases. It's not one simple gas. So if we're really concerned with loading in oxygen from the alveoli to the capillaries and offloading carbon dioxide at the lungs, then we have to really be concerned with the pressure of those individual gases, because they're going to move on their own. Right? So the pressure of a specific gas is called the partial pressure. And the total pressure, like the total atmospheric pressure, so here we see total atmospheric pressure, that 760 millimeters mercury is equal to the partial pressure of the nitrogen times the partial pressure of the oxygen plus the partial pressure of the water vapor plus the partial pressure of the carbon dioxide plus the partial pressure of any of the other gases. Okay, so the gas is going to diffuse across a permeable membrane. That means that the gas can physically go across the membrane, and it's going to go from a higher pressure to a lower pressure. So for each one, it goes from where its partial pressure is greater to where its partial pressure is less. And the greater that pressure difference, the faster the rate of diffusion. So let's have a look at how we calculate all these various partial pressures by looking at a table of them. So here's a table of our partial pressures, beginning up at the top with the partial pressure of nitrogen. That's N sub 2. So that's molecular nitrogen. This column is the percent in air. So in air, almost 79%, or 0.786 is the proportion, almost 79% of the air that you're breathing in and out is made up of molecular nitrogen. All right, so our sea level pressure is 760 millimeters of mercury. So that gives us a partial pressure. So over here, this column is all the listing of the partial pressures. Partial pressures. That gives us a partial pressure of 597.4 millimeters of mercury for the nitrogen. If we look at oxygen, about 21% of the air is made out of oxygen. So if we take 0.209 times 760 millimeters of mercury, that's going to give us 158.8 millimeters mercury as the partial pressure of oxygen. So P sub 02 is equal to 158.8 millimeters of mercury. Then the next highest is water vapor. Now, water vapor can vary. Sometimes you'll have a lot of water vapor. Sometimes you'll have drier air. So in Florida, we're used to having a lot of water vapor, but there can be varying amounts of this one. So the percentage is 0.4%, and that comes out to 0.004. Make sure you guys remember how to convert between percentage and the actual number. Okay, so remember, you've got to multiply by 100 to get your percentage. Right? So 0.4% is equal to 0.004 times 760 millimeters of mercury is equal to about 3 millimeters of mercury for the partial pressure of water vapor. Then we have the partial pressure for carbon dioxide. And carbon dioxide is found in very low amounts in fresh air. It would be 0.04% or 0.0004. times 760 millimeters of mercury is equal to 0.3 millimeters of mercury. And then we have the mixture of all the other gases. Right? So there's all sorts of other gases, argon, neon, there's a lot of different other gases that could be found in the air. And some of that may be related to impurities. So if you have some impurities, if you're breathing air, coming out of the back of an automobile, you're probably going to have some hydrocarbons in there as well. Okay, so there's all sorts of things that could be associated with this partial pressure of other gases. But if you add them all up, we come back to 760 millimeters of mercury. So if we add up 597.4 plus 158.8 plus 3.0 plus 0.3 plus 0.5, we come right around to 760 millimeters of mercury. So all the gases will actually behave independent of each other, and each one of them has their own partial pressure. All right, we're not done with the gas laws yet. There's one more that's really important for the actual movement of oxygen and carbon dioxide and nitrogen across your lung membranes, and this is called Henry's Law. So Henry's law states that the amount or quantity of gas that actually will dissolve in a liquid is proportional to the partial pressures of the gas and its solubility. So the higher the partial pressure difference, the more likely it is that the gas will diffuse, but not all of these gases are equally soluble in water. And remember, the lungs are covered on the inside with a layer of water. Your plasma is primarily water. The interstitial fluid is primarily water. So how soluble this material is in water really affects how well it will dissolve into your blood plasma eventually and into your blood cells. So the higher the partial pressure of a gas over that liquid, the more likely it is that the gas will go into solution and stay in solution. But also, you have to figure in the higher solubility. If it's more soluble, more of the gas will go into solution and stay in solution. All right, and not all these gases are equal. Carbon dioxide is found dissolved in blood at a much higher level than oxygen, because carbon dioxide is 24 times more soluble in blood plasma. Now, we do transport a lot of oxygen, but eventually when we see the transport of oxygen, we'll see that very little of that oxygen is actually transported as dissolved in the plasma. Most oxygen will get attached to hemoglobin. It won't be found out in the blood plasma. Carbon dioxide, on the other hand, is much more soluble in water, and so much more of it will be directly dissolved in the blood plasma. And then we come back to molecular nitrogen. All right, I'm going to flip back one. If we look at our partial pressures, you see that molecular nitrogen has the highest partial pressure. So if the amount that was dissolved in your blood was just dependent on the partial pressure, then you would be carrying around a lot more molecular nitrogen than anything else, but it's not. Molecular nitrogen has extremely low solubility in blood. It doesn't dissolve very well in water at all. So at normal atmospheric pressures, anywhere around 760 millimeters of mercury, we say that molecular nitrogen, N2, is physiologically inert. It doesn't exchange. It doesn't enter into the calculations at all. But there will be times when sometimes this molecular nitrogen can enter the blood. If we keep increasing the pressure, then nitrogen could eventually begin to dissolve in the blood. And there's one time point I can see, because I do it quite often, where this becomes a complicating factor. If you've ever heard of scuba, I have to put the S back on there, Cuba. No, scuba. Scuba diving. I can't put the S on there. There we go. So scuba diving, self-contained underwater breathing apparatus. The main thing in there is the underwater. As you go down underneath the water, pressure increases tremendously. In fact, the pressure usually doubles every 10 meters. That's about 30 foot underwater. So up at sea level, we're at 1 atmosphere, 760 millimeters of mercury. You go down 30 feet, or actually 33 feet, you're up to 2 atmospheres. That's just 33 feet underwater. If you go down to 66 foot, you're at 3 atmospheres. If you go to 99 foot, you're at 4 atmospheres of pressure. It increases greatly as you go underneath the water. So with this, the nitrogen, its partial pressure will keep going up and up and up very dramatically until it finally begins to go into solution. All right? So one problem with breathing normal compressed air at depth while you're scuba diving is that you could end up with something called nitrogen narcosis. Now, nitrogen can easily be converted into nitric oxides, and that's one of the neurotransmitters. And in fact, if you start getting high levels of molecular nitrogen or nitric oxides in the brain, it acts like an inebriating. You act as if you're drunk, and we call it nitrogen narcosis. You're narked out on nitrogen, and you can make some very inappropriate decisions while you're very deep underwater. And it can be very dangerous. Your reasoning ability becomes compromised. All right, so that's one thing that can happen as you go deep as you're diving. But then the other problem is nitrogen is normally not very soluble in water. So when you start coming up from depth, molecular nitrogen could pop out of solution inside your blood vessels. We call this decompression sickness, or the bends. Normally in scuba diving, you're constantly told to come up from depth very slowly, and that slow change in pressure allows you to get rid of all of this nitrogen gas by exhaling it. But if you come up too quickly, it could pop out in any of your major arteries. So if it pops out of solution and you have a gas bubble in your heart, you can have a heart attack. If it pops out of solution in your brain, you could have a stroke. All right, now those are pretty severe, and normally they're not going to come out of solution there, but it can cause problems. And so that's why scuba divers are always told to come up slowly, and the reason is you're changing pressures very slowly. All right, now let's look at the two gases that we normally think of as exchanging across these membranes. All right, and I'm going to pause here, and I'm going to come back, and we're going to start this in our second part of the video lecture on external respiration in the lungs.